This first slide shows the gummy triad models for the nuclei of the hydrogen and the helium atoms that were explained in Part 1. Multiple hydrogen nuclei become transformed into a helium nucleus when fusion occurs. The triangles represent triplets of up quarks, and the spheres represent virtual intranuclear electrons. These electrons are virtual because during reverse beta decay, also called proton-electron capture, an electron is pulled into the nucleus and gets transformed into other entities. There are no actual electrons in the nucleus. However, when beta decay occurs, those same entities reform into an ejected electron. So the virtual electrons shown are referred to as quark electrons, and they simplify quark counting. The gummy triad models are not shown to scale. In point of fact, electrons are close to being infinitesimally small points. Observing the model, we can see that a helium nucleus consists of 4 triangles and 6 quark electrons. But 4 hydrogen nuclei only provide 4 triangles and 4 quark electrons. So an additional 2 quark electrons are needed to form the helium nucleus. But where do quark electrons 5 and 6 come from? This next slide explains stellar fusion, and it shows that quark electrons 5 and 6 come from additional protons 5 and 6. But that leaves behind 2 unpaired quark triads, and these quark triads have enough residual force to quickly create electron-positron pairs from nothing. The created electrons will restore protons 5 and 6, and the 2 positrons will collide with free electrons and produce gamma rays. There should always be gamma rays produced during fusion unless the positrons aren't being created and released. Once the stellar fusion reaction has been started using 6 hydrogen atoms, it only takes 4 hydrogen atoms and the 4 protons from the hydrogen nucleus to create the next helium atom. The fusion process is thus sustained and a star is born. This slide explains the somewhat different fusion process used in a hydrogen bomb. The fuel used is what Star Trek refers to as dilithium. The correct name is lithium deuteride. During the fusion reaction, lithium deuteride plus a neutron turn into 2 helium atoms plus a neutron, and the regenerated neutron starts a repetition of the cycle. The gummy triad model for the lithium deuteride nucleus is shown in 2 parts, a lithium model and a deuterium model. From part 1 continued, we saw that the gummy lithium nucleus provides 9 quark electrons and 6 triangles, while the deuterium model provides 3 quark electrons plus 2 triangles. That's a total of 12 quark electrons and 8 triangles that get rearranged during fusion. The catalyst for fusion is a neutron with its 2 quark electrons and 1 triad or triangle. The neutron causes the lithium nucleus to split into a tritium nucleus and a helium nucleus. The deuterium nucleus then combines with the tritium nucleus to form another helium nucleus, plus a free neutron. This free neutron starts a repetition of the cycle, otherwise known as a self-sustaining chain reaction. To get an enhanced chain reaction, additional tritium can be included in the weapon. The 12.3-year half-life of tritium adds a quasi-safety factor to hydrogen bombs, because the tritium needs to be replaced periodically to keep the weapon viable. The next set of slides are all about the fusion that is yet to be, meaning the several types of experimental fusion reactors and fuels that are out there. But all approaches have the common goal of outputting more power than is consumed, and heating up fuel to plasma temperatures consumes a lot of power. Fortunately, experiments are getting closer to reaching this goal. For those interested, here is the recipe to create your own fusion fuels by simply knowing the number of quark electrons and triads in your element or fuel of choice. The numbers going into the reaction just have to equal the numbers coming out of the reaction. In part 1, it was explained how to create this recipe table using an algorithm designed for the gummy models. That algorithm is shown at right. The total number of triads equals the sum of the fuel's protons and neutrons, and the total number of quark electrons equals the number of protons plus double the number of neutrons. Part 1 used this algorithm to count and chart quarks for all known isotopes of an element, elements being fusion fuel in our case. And the chart also indicated which of the isotopes were stable, non-radioactive elements. This is good to know because radioactive isotopes are less desirable as fuel. But there are exceptions. Tritium is used as fuel and it is radioactive, so it's been marked with a radioactivity symbol. This algorithm slide has also introduced a new summary table at the bottom for most elements that are used as fuel in fusion experiments. Next, we have a slide using gummy nuclear models to review the use of deuterium and tritium as fuel in several types of experimental reactors. Note that the models show 5 triads and 8 quark electrons going into and coming out of the reaction. There are no catalysts left over, so there is no chain reaction to worry about. Basically, control of the input fuel flow rate throttles the amount of energy being released. The advantage of using deuterium and tritium as fuel is that they require lower temperatures to reach plasma temperatures and ignite into fusion, compared to other fuel choices. The disadvantage is that the output from this fusion is a leftover neutron, and a neutron is really difficult to shield against. Tokamak fusion reactors use magnetic fields within a toroidal containment vessel to confine plasma streams that are trying to escape. What doesn't get confined are the neutrons, and they accelerate the decay of the confinement vessel. If used as a power plant, the shielding against the neutrons would have to be sufficient to protect the human work crews. The laser fusion reactor at the National Ignition Facility, or NIF, just combines these two hydrogen gases in a pellet as fuel. Then multiple lasers in the high-energy blue UV end of the spectrum heat up one pellet at a time until fusion occurs, and then the next pellet gets its turn. The projectile fusion reactor at first light accelerates a small fuel cube into an impact wall and produces about 50 fusion neutrons. The small cube has a built-in self-forging lens that, upon impact, brings the confluence of deuterium and tritium to fusion temperatures and densities. To produce electrical power, larger cubes would be repeatedly fed into an acceleration device, and the neutron heat would produce steam to power a generator. This next slide has models to help us review the use of deuterium and helium-3 as fuels in a different type of experimental fusion reactor. Again, note that the models show 5 triads and 7 quark electrons going into and coming out of the reaction. So again, no catalysts are left over and no chain reaction to worry about. And fuel flow controls the amount of energy being released. The advantage of using deuterium and helium-3 as fuel is that the output from the fusion reaction is a leftover proton that is really easy to shield against because it's charged and can be controlled with electric fields. The disadvantage is that the fuel must be heated to higher plasma temperatures in order to ignite fusion. A field reverse configuration fusion reactor, or FRC, uses induced magnetic fields to contain the plasma, meaning self-generated magnetic fields. Because of that, and the relaxed shielding constraints, they can be scaled down to the size of an SUV, which also gives the design a unique niche for rocket designs. Princeton Fusion Systems is the primary developer of the RFC design. In this final slide, there is a very busy gummy model that helps us review the use of boron and protons as fusion fuels. The model shows 12 triads and 18 quark electrons going into and coming out of the reaction. Again, no catalysts are left over and no chain reaction to worry about. Once again, controlling the input fuel flow controls the amount of energy being released. Also note that a new boron row has been added to the bottom of the element table. But the table skips over lithium and beryllium. That's because only boron has the advantage of producing relatively harmless alpha particles. From part 1, we recall that alpha particles are the easiest radioactive particles to stop via shielding. The disadvantage of using boron as fusion fuel is that it must be heated hotter than any of the other fusion fuels. TAE is the primary developer of boron fuel fusion and uses an elongated version of an experimental RFC fusion reactor with magnetic end caps. And that's it for fusion. Thanks for checking out my YouTube videos.